So, in the last class we started a new topic which is on eddy current testing, and then we saw few laws which govern this particular technique, and then finally we derived a parameter called impedance, and then I told you this is the parameter that we were looking for, and this parameter can be used for doing eddy current testing. Okay. So, let us continue on that, and then we will see how this impedance that we derived from the last lecture, how this can be used to eddy current testing. Okay. So, this is what just to give you a quick recap, this is what we did finally. We derived this particular parameter Z or impedance, which is the total resistance to flow of current in a conductor, which contains both a resistive element as well as an inductor. Okay. So, if you have a combination of both inductance and resistance in a circuit, the total resistance to the flow of current will be given by impedance. Okay. So, this is the parameter that we derived, and you could also see from this, this impedance will have some phase lag theta with respect to the current through the resistor. Okay. So, let us first get an expression for Z, and then we will see how it can be used for eddy current testing. Okay. So, this will be our topic today. So, for this you need to again go back to Faraday's law, which we already discussed, and there we saw that the induced EMF, if you call it VL, is this, wherein d phi dt is the change in the magnetic flux, phi be the magnetic flux. Okay. Now, when I say the total impedance or the total resistance to the flow of current is Z, then through Ohm's law you can write this, okay, because this is what Ohm's law tells you. If I be the current and if there is a resistance to current, then voltage will be I into the resistance, and in this case, as I said, the total resistance is the impedance. Okay. Now, if you take VL in terms of current, okay, because current is a parameter which can be easily measured. On the other hand, magnetic flux cannot be easily measured, like what you can do for the current. So, it will be convenient to convert the magnetic flux in terms of the current. If you want to do that, then you have to use this relationship. Phi is given by L times I, where L is the inductance and I is the current. Okay. So, we can derive for a given conductor or for a given inductor, this L is constant. So, this will be 0, and as a result d phi dt will be equal to L di dt. So, L is constant, dl dt is 0, that gives us d phi dt equals to L di dt. So, we can write VL in terms of the current or the change in the current di dt in this fashion. Okay. Now, coming back to the Ohm's law, we know it is V equals to IR. This is the case where you have only a purely resistive element carrying the current, but when you introduce the inductance also, then this induced EMF will also come, which is VL, and we have seen why this negative sign, because this induced EMF is opposed to the primary magnetic field which induced the current, and that is why the negative sign. Okay. So, now we can write this, okay, and from this we can derive an expression for the impedance Z. Okay. So, let us say this current I is a sinusoidal function. Okay. So, that means now we can write and V L, the expression of V L we have already got, that is L d I dt. I is I naught sin omega t, and from here you can also derive d I dt. Which is this. So, now if you write it here, so we have an expression like this. Okay, which looks very similar to the Ohm's law that we started with in this case. Okay. So, that means if you replace this parameter with this Z, it gives you the same relationship. Okay. So, that means Z is equal to Okay. So, this is the expression for Z. We can simplify a bit by taking a parameter omega L equals to X L, wherein X L is known as inductive reactance. Okay, L is the inductance and omega is the circular frequency, which is 2 pi f, f be the frequency. So, this inductive reactance is nothing but the reduction in current flow or the resistance to current flow due to inductance. Okay, so finally, we have an expression for Z like this. Okay. So, that means the magnitude of Z is this, or if you break off X L, then it will be this. Okay, and it can also be plotted in this fashion with in terms of XL and R. So, as you could see Z is the sum of R and XL. So, it will be a vector like this, okay. And this is the phase lag or the phase angle that we talked about before, if you remember, which is here, okay. This phase lag between the impedance and the resistance, that you can see here also, okay. So, this is how Z can be broken in terms of the inductance and the resistance, or in other words the total opposition or total resistance to the flow of current, which is impedance, is a combination of inductance and resistance, okay. So, based upon this relationship and based upon this particular plot, something called an impedance plane is constructed, and that is what is used for doing eddy current testing, as we are going to discuss right now, okay. So, let us see how this impedance plane can be used to do eddy current testing. So, in eddy current testing, what you have, as I have told before also, you have this coil which is carrying the current, which is carrying an alternating current or a changing current to induce the eddy current onto the sample. So, here nearby, if you have a conductive surface, you will have this eddy currents forming, okay, and this will have its own magnetic field, the induced current, and that is opposed to the primary magnetic field that we have already discussed, okay. And then you have a detector over here to detect any change which may come in this coil, okay. So, that change will come due to the presence of a discontinuity. That means, if there is a defect on this surface, and due to that defect, if there is a change in the eddy current, due to that change there will be a change in this coil also, which will be detected by this detector, okay. And in order to sense this change, this parameter that we derived just now, impedance, will come into picture. So, what is going to happen when you bring this coil close to the sample surface? When it is close enough, then these eddy currents will start, okay. So, the distance between this probe and the sample surface is known as lift off. And the moment the induced current or the eddy currents starts flowing in the surface, so the eddy currents or the induced current are coming out from the current or from the energy which is flowing in the primary coil, right. So, since the energy is taken away from this coil, okay, that will be reflected in an increase in the resistance, okay. So, let us say first you have this lifted away from the sample, that means your coil is in the air, and as you decrease this distance or as you reduce the lift off distance, then the resistance will increase, because as I said, now the eddy currents will be induced. So, some energy will be drawn from the primary coil, and that will manifest in terms of an increase in the resistance. Okay. And the inductance or the inductive reactance will decrease, because now you have eddy currents, and these eddy currents have their own magnetic field which is opposed to the primary field, and due to that fact the inductive reactance will decrease and the resistance will increase, as I said, because you are drawing energy from the primary coil. Okay. So, you will get a curve like this as you bring the coil close to the conductive surface or close to the sample. Okay. So, that is why this curve is called as a lift off curve. This is what is going to be shown on that impedance plane, because this XL and R, as I said, this constructs the impedance plane, and as you bring the coil close to the sample surface, this lift off curve is going to be shown on the impedance plane. Okay. Now, depending on whether there is a defect or not, you will see a signal here in this impedance plane in this manner. Okay. Let us say there is no defect on the surface is defect free. So, there will be no change in the eddy current, and as a result there will be no change in the impedance of the coil. Okay. So, you will not see anything apart from this lift off curve. So, as you move along the surface, the signal will move back and forth along this only, along the lift off curve only. Okay. Now, if you have a defect at some point on the surface, and the moment you move the coil or move the probe over that defect, the eddy currents will be affected, will be changed, and due to that there will be change in the impedance of the coil. Okay. So, let us say there is a crack. So, there is a small opening, and because of that opening, when you move the probe over the crack, the eddy currents will reduce. As a result, the resistance in the coil will reduce, because your extent of eddy current is reducing on the sample surface. Okay. So, that means this will tend to go back towards lower value of R, and now that you have less eddy currents flowing because of the presence of the crack. So, the magnetic field of the eddy currents will also reduce, and as a result the XL or the inductive reactance would also tend to go up. Okay. So, that means the crack signal will be like this. So, you will immediately see a spike like this the moment the coil or the probe encounters a defect. Okay. So, this is the crack signal, and that is how this will indicate the presence of a defect on the sample surface. Okay. So, this is the basic principle of this particular technique, which is based upon this impedance plane, which we derived with the help of two laws primarily. One is Faraday's law and the other one is Lentz's law, and then we also took the help of Ohm's law and got an expression for this. And then once you construct this impedance plane, then in this fashion, as we discussed, you would be able to get a signal out of a defect in this fashion, like a spike over the lift off curve, which will indicate that there is some discontinuity on the surface, due to which there is a change in the coil which is being detected in terms of this impedance parameter. So, that is what this detector is going to sense or going to detect and indicate in this fashion. Okay. So, this is how the whole technique works based upon this. Okay. Before we move on, I should also tell you that when you talk about inductance, as you would have realized by now, this whole technique of eddy current is based upon inductance. Inductance could be self inductance and it can be mutual inductance. Self inductance is when it is in the same circuit, when you see the change in the voltage due to inductance in the same circuit or in the same conductor, then it will be self inductance, wherein in case of mutual inductance there will be a second conductor. Okay, so, in this fashion. So, let us say you have a circuit like this, where you have this resistor R1 and the inductor L1. So, this is circuit 1 or conductor 1, and if you bring another conductor close to it, let us say that is carrying a current I2 through this R2 and L2. So, these two conductors, when you bring them together, will have a mutual inductance effect on each other. Okay. So, conductor 1 will induce some current on conductor 2, and conductor 2 in turn will induce some current on conductor 1. Okay. So, if you write it in terms of this inductance or the magnetic flux which generates this induction. So, let us say in the circuit 1, the magnetic flux phi 1 will be L1 or L11 I1. So, that is due to the current I1 which is flowing in conductor 1, plus it will have some induced EMF also, which will come from the second conductor. So, that will be L12 I2. Okay. Similarly, in the second conductor, if you see, the magnetic flux phi 2 will be the current which is flowing into it, due to that L22 I2 plus the inductance which is coming from conductor 1, which is L21 I1. Okay. So, this parameter L12 and L21 is known as mutual conductance, which we will call as M, mutual, it is known as mutual inductance. Okay. So, if you replace this now with M in these two equations, then you have, now we can simply call this as L1 I1 plus M I2. Similarly, phi 2 will be L2 I2 plus M I1. Okay. So, this is the phenomena of mutual inductance, and the eddy current testing, as you would have realized, is based upon mutual inductance. Okay, now let us come back to this lift off curve, okay, because that will be our basis for doing eddy current testing. So, whenever we talk about something related to eddy current testing, this impedance plane or the lift off curve has to come into picture. So, we will have to come back to this again and again as long as we are discussing this particular topic. Okay, so, this is the lift off. Now, this will this lift off curve as to how far this resistance will increase and the inductance will decrease, that will depend on the sample properties, particularly the conductivity of the sample. Okay. So, if the conductivity of the sample is high, that means it has lower resistance, so it can accommodate more current. So, for a higher conductivity sample, it will draw more energy or more current from the primary coil, and as a result of that you will see a larger increase in the resistive component of the coil. Okay. Similarly, if you change the conductivity, if you reduce it, the reduction in the resistance of the coil will be lower, right. So, there is an effect of conductivity. So, as you increase the conductivity, your resistance will increase more and more, and that is why this conductivity curve will be like this. So, if conductivity increases in this direction, the change in the resistance and the inductance will be along this curve. Okay. So, this conductivity curve is obtained because for different materials the lift off curves will be like this. And if you join the endpoints of them, you get this conductivity curve. Okay. So, this gives you a total picture in terms of both the impedance as well as the conductivity of the sample. Okay. So, please keep that in mind, because if you have a highly conductive sample like copper, the coil will become almost like purely resistive, because the change in the resistance of the coil will be very high. And similarly, if you have a lower conductivity sample, the change will be lower. Okay. So, this is the effect of conductivity, and that is how you get a conductivity curve over the lift off curve. Okay. So, this is all I will have for today, and rest of the things related to this we will discuss in the next class. Thank you.